Okay, so in problem number 6, we're back to Lewis acid and Lewis base. We learned that a base, by Lewis definition, is a pair of electrons. An acid is the compound that accepts that pair of electrons. So if you look at the CH3, CH2, Cl, so the Cl has those electrons. So it's going to make a new bond between Cl and alumina that has an empty d orbital to make a bond between from carbon to Cl and to alumina. Now, if you recall, by doing this, alumina has 4 electrons, so it would be formally charged negative. Should have only 3. Cl lost that electron. Now it has 6, so it's positive. And it makes sense because here we don't have any charge. Now we have a positive and negative charge. In the second case, it's an alcohol. It's a little bit small, but it's an oxygen. And we have BF3 here. Maybe I'll draw it again. BF3. So again, electron make a bond to boron. Electron make a bond from oxygen to boron. A new bond forms. Oxygen losing that electron, so it's going to be formally positive, charged positive. And boron, accept that electron in d orbital would be negative. In the case of the carbocation, so it's a carbon with positive means electron is missing. Electron is missing. So this would be not the acid. And when we're looking at the water coming in, so water has electron, oxygen has electron, make the bond, showing it as an arrow. So the bond comes from the oxygen to carbon. So this oxygen now lost that electron would be positive as formal charge. And carbon accepting that electron now is neutral. Again, the balance is there. We have a positive from carbon. We have a positive from carbon here. Now the positive charge went from carbon to oxygen. This is a better structure because all the elements have 8 electrons. The next set of reactions and question number 7 is very similar. So we have a base, which is electrons. So we have a base here, base in nitrogen, base with electron to pi bond. So pi bond is basically an electron. So we're looking at that acid-base reaction. So oxygen make a new bond. We don't have a fully positive charge, but we have a partially positive charge. So we have a partially positive charge hydrogen and partially negative charge chlorine. So now, because the hydrogen cannot have 2 bonds, electron between hydrogen iodide goes to the iodide. So the product at the first part is O with 2 H's. Now the O would be positive. And iodide, basically gaining those 2 electrons, become I minus. The other reaction is between the amine. Amine has electron. Again, we have a partially negative and partially positive. So partially positive is the acid. So we have a bond between nitrogen and H. Electron between H and chlorine goes to chlorine. So now we have a nitrogen with 4 bonds. So it would be formally positive. And Cl, by gaining those 2 electrons, become negative. So again, I didn't talk about it, but again, we have a base, we have an acid, we have a conjugate acid, conjugate base. The last but not the least is a double bond, a pi bond. So a pi bond is actually a base. And again, HF fluorine is partially negative, H is partially positive. A bond formed between this carbon is symmetrical. Between the carbon now, this carbon, because it's attached to the pi bond, and H here. So if you move the electron this way, so now the carbon that lost the pi bond would be positive, and that's a conjugated acid. And if gaining this electron would be negative, would be the conjugate base. So this was page 3. Okay, we're on page 4. So in page 4, we still have following the path for Lewis acid and Lewis base and using curved arrow. So Dr. Solomon is asking us to look at the arrow and see what we make. So if you look at the oxygen again, the oxygen has that extra electron. The arrow didn't show up very well here, but the arrow goes from oxygen to boron. Remember, boron has an empty d orbital. So there's a new bond formed between the oxygen and boron. So boron still has the 3 fluorine. Oxygen now would be positive, and boron would be negative formally charged. The oxygen and ether and BF3 can make the same kind of reaction. So the oxygen is basically joining the electrons to the boron, make a bond to the boron. So oxygen now losing that electron is a positive. Boron, by gaining that electron, is negative charge. So this was the first one was a ketone. The next one was an ether. The one after that is not a ketone. Remember, if it has an OH, this is a carboxylic acid. So oxygen and a carboxylic acid can also, is a base, can react with the H, and the electron between the H and Cl goes to the Cl. Now, oxygen would be positive, and the H comes from the HCl, comes here, and Cl gaining that extra electron would be negative. Again, so these are back to acid-base reaction. So this is a base, acid, conjugate base. The last one is I always ask a student to look at the carbon-lithium bond as very polar. And we can give that electron actually to the carbon, makes it easier to see. So carbon now would be negative as a base. Basically grab the H from the alcohol. So become an alkane. Here we have 1, 2, 3, 4 carbon. 1, 2, 3, 4. And O losing that H basically become O minus. So if the alcohol was the acid, this would be a conjugate base, and this was the base, so this would be a conjugate acid. Question number 9 is very similar, so it's asking us to look at OH, which is sodium hydroxide, for all of these reactions, or some of them actually, the first two. So we have an OH, again O and an O, these are the base, so they're going to react with the proton. So we can draw that arrow to this H. I forgot to draw the second arrow. So the second arrow shows that electron goes from between the H and O, goes to the O. So the O would be negative, and O minus H now would be water, basically, by gaining that from the conjugated acid. Same thing here with this sodium hydroxide. This O minus react with the H, grab the H, basically. Again, I forgot the arrow, so this arrow should be showing electron goes to the oxygen. So we're going to have the conjugate acid as water and conjugate base with the O minus from this sulfonic acid. The next one, we're going to look at the sodium methoxide. And remember, when we have sodium hydroxide, sodium doesn't really play any role. OH minus is the one that we're going to pay attention. So OH minus is the base. Same thing here. So this O minus from sodium ethoxide is a base. React with the H. And remember this H is partially positive. It's acidic. The bond between H and carbon goes to the carbon. So the carbon now is negative. Carbon is negative. And O as an O minus, grab that H, so this becomes conjugate acid. Part D, carbon is the negative. Carbon is the negative, is the base. Grab the H, and this H, again, as I said before, is a partially positive. So this becomes from a negative to neutral, so it makes basically ethane. And the carbon here, gaining that electron, now is negative and is conjugate base. Again, we have another carbon negative here as a base. Grab the H from the alcohol. This was from alkyne. This is the alcohol. Become an alkane, conjugate acid. And O, by gaining that electron, become the conjugate base. Okay, on page 5, couple problem. One of them is similar to what we did before. So we have a carbon negative. So carbon negative is a good base. Grab the H from here, and the electron between the H and oxygen goes back to the oxygen. So we would have a alkyne as a conjugate acid and O minus as a conjugate base. Now the problem 11 and 12 is something we learned in general chemistry. So we were told that Ka of formic acid is 1.77 times 10 to the negative 4. We remember that pKa is negative log of Ka. So negative log of 1.77 times 10 to the negative 4 is 3.75, and we need to remember something with sig figs. So that's really about 3.75. So the key to remember again for this question is pKa is negative log of A. On the other hand, if you have a pKa, Ka would be equal to 10 to negative pKa. So for this second question, if the Ka is 13, Ka would be 10 negative minus 13. The next series of question number 13, we have two acids. One of them has a pKa of 20, one of them has a pKa of 10. Obviously, the lower pKa is a stronger acid. So lower pKa usually is a stronger acid. So this is a smaller pKa, so this acid Hb would be stronger than Ha. Now next question number 14 is interesting. It's a synthesis question. So we were asked to look at a carbon bonded to a T, which is the isotope of hydrogen. How will we make that? So if you're going sort of backward, we know, so this is my backward question. Backward. We know that if I have, we learned in the previous problem, if you have a C minus, and if I have a water, so this water hydrogen is replaced with T, so it's the same thing. So if I have these two, I can say this is a good base and this is an acid. So we can have a reaction between the base and the acid. So reaction between these two are going to make that. That's what the backward is. Now how would I make this one with the C minus? So that comes from CH actually. It comes from the CH. And this is an acid. We need a base. So amide, what we call NH2 minus, sodium amide is a good base. Remove the H. Electron goes here to make C minus. C minus react with the isotope, hydrogen isotope, heavy water, to make the product we're looking for. Let's look at this one. So here we have a O and a D, O and a D. So how would we make that? We remember the O minus is a base, so it's a good base. If I have a substitute D water, heavy water, so I can make a reaction between the O minus and the D. D would be the base acid. So this combination of these two make this one. Now how would I make the O minus? So if I have the O minus comes from the alcohol. So if I have the alcohol and add sodium amide to it as a base, I can remove the H. Then this becomes O minus. O minus react with the DOD to make OD. The same thing for the last ones. We wanted to make an O and a D. We want to make an O and a D. So how would I make an O and a D like we did here? So we need an O minus, and the O minus can react with the D2O to make OD as a base and acid. How would I make the O minus? So O minus comes from the alcohol. So alcohol we can again react it with some base like sodium amide to make the O minus. O minus react with the D to make OD.